Hello, welcome to the introduction lecture for chemical engineering. My name is Aidong. I'm one of the academics in the chemical engineering panel in the department. So the purpose of this lecture is to give you a brief introduction about what chemical engineering is, what engineering challenges chemical engineering addresses, and also as an undergraduate student, what courses you will take to train yourself to become a chemical engineer. We will also have a brief look at the future of chemical engineering. So to look at what chemical engineering is about, we can start by considering the products that is made by chemical engineering. So the first one I show here is something we eat. I hope this doesn't surprise you because chemical engineering contains food processing or food engineering. And also what we drink, that points to water purification and water processing. What we burn, the production of fuels. What we put on textile, and what we take when we're not feeling very well. This is the medical products. And of course, chemical engineering makes a lot of other chemicals and materials. For example, the things we use for decorating, for driving, and for building the houses or other construction. So it also makes what we play, such as sports, things we use for sports, for music, and arguably most important for some of us, this one. So, but in order to make all of these, we will have to build chemical plant or chemical factory. So this one is a oil refinery, a picture taken in the night, which looks quite spectacular. This is for making different types of fuels. And this one is very different. It's smaller but much neater, I guess. It's a pharmaceutical facility for producing medical products. So we have seen what chemical engineering makes and what it builds, but what is chemical engineering? I would say it is an engineering discipline which focuses on transport and transformation of materials, accompanied with the transport and transformation of energy. And what makes chemical engineering really special is that we do these things on materials and energy primarily at molecular level, and which marks a key difference from, for example, civil engineering or mechanical engineering. Okay, so at the core of chemical engineering is the concept of reactors, and we have different types of reactors. If we start with the conventional chemical reactors, so here I have got an example, which is the Haber-Bosch converter for producing ammonia from nitrogen and hydrogen. I put it up here because it is one of the earliest reactor designs operating at high temperature and high pressure with catalyst. So, and the other one I show here is the something taken from oil refinery, is a fluidized catalytic cracking unit, or FCCU, which is for producing short chain molecules from long chain hydrocarbon. So the reason why I put up these two reactors is because they do carry some historical importance. If you look at Haber-Bosch reactors for making ammonia, and many people believe is that this kind of chemical synthesis of ammonia enabled by the Haber-Bosch process has played a very important role in food production, because ammonia is a major fertilizer, and this has been very important for sustaining food supply for the growing world population. And what about FCCU? People who are familiar with the history of Second World War might have seen the statement about the importance of the fuels produced by this technology in the victory of the British and US Air Force, because of the supply of high quality fuels required for the air forces. So, but of course, reactors are not just chemical reactors. There are other types. So, for example, electrochemical reactors, which would involve the conversion between chemical and electricity, and this includes electrolyzers, which converts electricity into chemicals, and fuel cells, which go the other way around, converting chemical energy into electrical power. And these kind of reactors are becoming increasingly important in the context of generation and utilization of renewable and clean energy. So then we have these bioreactors. It's a very important type of reactors. Here I have an example of a fermenter. And some of you might know that a key microorganisms used by a fermenter is a yeast. And if you zoom in, you can see within these cells you have a complex biological machineries which can be used to convert substrates like sugar into valuable products like alcohol through fermentation processes. And another example is photobioreactor, where microalgae is cultured. So these are unicellular microorganisms, again with a interesting set of bio machineries which can convert CO2 into biomass through photosynthesis, and then the biomass can in turn be converted to useful products. So, but of course there are many other examples of bioreactors. I'm not showing more examples here, but just to say that this biochemical engineering branch of chemical engineering is becoming more and more important in many areas. So just to make things a bit more complex, now we can even have a reactor which combines the bioelectrical and chemical. So an example here is a microbial fuel cell, where you have microorganisms in the anode chamber of the reactor converting substrate into electricity, which can be, for example, applied in recovering the energy from wastewater. So these are the reactors. But in chemical engineering, we certainly need reactors, but the operation of reactors will need to be supported by some other so-called unit operations, such as for mixing, separation, heat transfer, and pressure change. And in fact, the concept of unit operations was formed in early 20th centuries by pioneering chemical engineers such as Professor Arthur Lita, and the formation of this concept of unit operations somehow marked the birth of modern chemical engineering. So I have got an example here. If you have taken GCSE or A-level chemistry, you would recognize what this is. It's a distillation device. You might have played with it in your lab in your high school, and this, is linked to a key separation unit operations. So it's a distillation column. So in chemical engineering, we do something very similar to what you have seen here, but just in a kind of bigger, larger scale. So we have seen reactors and unit operations, but one complexity of chemical engineering is that we have to link these different unit operations to form a whole process, a whole plant. So I think the example shown here is again ammonia production. So this is the Haber-Bosch reactor we have seen earlier on, but you can see as a whole ammonia plant is much more complex than just the reactor alone, right? You have here you have the reforming of natural gas, the further conversion of CO2, conversion of carbon monoxide into CO2 and hydrogen. Here is a removal of CO2, and then you have the finally the ammonia synthesis with hydrogen and nitrogen. And here you have the separation of ammonia product. As you can see, for the whole plant to work properly, you need to have the unit operations to operate in unison, if you wish, so that we can run a productive and stable process. So the design and operation of such a complex process certainly requires a lot of thinking, a lot of careful design, a lot of careful decision making. So what are the problems then a chemical engineer is expected to solve in the daily life? Well, I'm sure this list wouldn't really surprise you based on what we have seen earlier. So we have the design of unit operations, design of the complex process and plant, looking after operation and control, and also design of products. So, but how would we judge whether we have done a good job on any one of these? Well, we need to look at a number of objectives. So whatever we do, we have to ensure safety. Safety is always the most important thing for any engineering, but particularly for chemical engineering. And we always try to improve the efficiency of materials and energy, and to make things implemented in industry, it has to be profitable, so it should have a good economics, and we do need to look after our environment and as well as the social sustainability. So you can see we have multiple objectives, which means chemical engineering is really a very, very demanding job. So how we can make our students capable of handling such complex jobs? Well, this has to be done. We come back to the fundamentals. This has to be done by going through a rigorous training. So in Oxford, in this department, if you look at a 4-year program, going from the first 2 years with common engineering training, and then into the 3rd year and the 4th year, where students can get a bit more specialized in one or several areas. So the students will be taking a number of courses which would address all the important aspects of chemical engineering, either on the material side or on the energy side. So these are the specific courses, but don't forget that in year 1 and year 2, there are common courses in mathematics and numerical methods, engineering and society, and also thermodynamics, which are useful for all the engineering disciplines, but of course they are also very, very important for chemical engineering. And then moving on to year 3, thermodynamics will be learned further, which forms a very important foundation for many aspects of chemical engineering. In addition to these different courses, we do have 2 major projects throughout the 4-year program. So in the 3rd year, there will be a design project. This is a group-based activity. So at the moment, we're running a design project with our 3rd-year student in the area of carbon capture and utilization, and particularly it's about designing a chemical plant which can turn CO2 into methanol. Okay, so it's a very interesting topic. And then in the 4th year, there will be individual research projects, and every year there are a number of chemical engineering oriented research projects offered to our students. So these courses and projects will, we believe, get our students well equipped for the chemical engineering career, but they will be educated not only for to become the workforce today, but rather to prepare them to meet the demand of future challenges. So and here I guess we can look at a major challenge from climate change is, I guess, widely recognized as a major challenge for our society in the future. And in the UK, for example, we also face aging population, and which points to the challenges in the future health. So we have environmental health, we have human health, and chemical engineering should certainly make a great contribution to address the future challenges in both areas. So how we do that? Well, I guess there are two different things we can do. One is for the products or services the chemical engineering is providing now, we can try to do them better, right? So the same products, same services, but we try to do them better. For example, in order to produce certain chemicals or material, so instead of processing fossil resources, we try to look at something greener to process, such as biomass. Okay, so in a sense, we can deliver the same chemical, same material, but by processing a different feedstock. Okay, or we can be cleaner in how we process things by reducing emissions, reducing energy consumption, water consumption, for example. Okay. So this is about doing the things that we're doing, but in a better way. Another thing that chemical engineering can do to meet the future challenges is to start offering something different from what we're offering now. And I have got a number of several examples taken from the research which is undertaken by our colleagues in chemical engineering here. So the first one shown here is a chemical-based energy storage. So the story here is with the increasing penetration of renewable energy into the energy supply, one of the problems we have to face is that there is great intermittency or variability in what solar or wind energy can be made available to us. So how do we deal with this intermittency or variability? Well, one of the approaches is by energy storage. So when there's a lot of energy available, we try to store it somehow, and then when there's deficit, we try to offer energy from the storage to meet the demand. And chemical-based energy storage is one of the energy storage technologies, and particularly useful for long-term storage and storage in a large volume or large quantity. Okay, so that is one area. And another area I show here is something called negative emission technologies. So this is about dealing with greenhouse gases. So we all know that we need to cut down the greenhouse gas emissions so that we don't get into very dangerous climate change, which is certainly true, very important. But many people believe that we might have already got too much greenhouse gas in the atmosphere, particularly CO2. Okay, so the task of negative emission technologies is to take the CO2 which is already in the atmosphere out. Okay, and this can be done by different technologies. And what is shown here, we have three things here. One is what is called accelerated weathering of rocks to promote reaction between the CO2 in the air with some minerals. And this one is direct air capture. It's kind of separation process. And here is the bioenergy with carbon capture and storage. Basically, we grow trees, for example, and then we turn biomass into energy. But in that kind of power conversion process, we capture CO2 emitted. Okay, so and all of these, you can see, they are very, very closely related to chemical engineering. And finally, so if we move from environmental challenges to human health challenges. So one example I show here is about stem cells or cell therapies. So you might have heard of the good things that stem cells can do. through cell therapies. But a fundamental requirement to do cell therapy is that you need to have a sufficient amount of cells in good quality. So if you start with a rather limited number of cells, you definitely need to go through something called cell expansion. And this can be done by kind of this biochemical engineering techniques, particularly this biochemical bioreactor, and which is capable of taking the small number of cells and to do the cells expansions to supply the cells in the required quantity and required quality to enable cell therapies. Okay. So I think I'm coming to the towards the end of this introduction. We talk about chemical engineering futures, and perhaps we can ask whether chemical engineering is your future. Well, I hope through this lecture you have seen some exciting future offering that chemical engineering can give to deal with future challenges, ranging from environmental side to the human health side. And I also hope that you feel some of the fundamentals of chemical engineering is interesting to you. And on top of this, if you are also prepared to do the hard work, namely taking the courses important for chemical engineering, then perhaps you can really consider chemical engineering as one of your future career options. Okay, so with this I will stop. I hope you have found this introduction useful to you. If you have any questions, please do feel free to contact me by email. Thank you very much.